when a graph is removable or when it's not removable. Then we're going to stop and we're going to practice this a little bit on a separate assignment from your book. I will, if we have time, I will take questions from your homework yesterday if you guys got a start on that. F of x is equal to 1 over x squared. This is what the graph looks like. Has unbounded behavior. So we consider that to be not a continuous graph. If I were to follow this graph, if I were to pencil it in as I go, I would physically have to pick up my pencil and move it over here to trace the other part of the graph. Not continuous. If I have to lift my pencil, it would be considered not continuous. Is it removable or non-removable? Well, it would be non-removable because in order to get these graphs to meet, we'd have to change the graph a lot. It wouldn't be just a simple moving one point over or coloring one point in. This example, also discontinuous, because if I trace this graph, I would have to lift my pencil when I get here, jump to the other side of the break, and continue on the other side. Not continuous. We call it discontinuous. Removable or non-removable? Removable, because all I have to do is just fix that one little point, color it in, and then it's removed. Then it would be a continuous graph. So we say it's discontinuous, but we call it removable because all I have to do is fix that one value. I have to fix the value of x is equal to 9. So I just need to fix that one point, and it would be a continuous graph. So it's removable at x equals 9. F of x is equal to, what kind of graph is this? What do we call this? Piecewise, two pieces. It's made up of a line on the left, a parabola on the right. Is it continuous? Continuous, yes, obviously it's continuous because it says right there it's continuous. But if I trace this graph, I do not have to lift my pencil to get from one to the other. The continuous curve. We say it's continuous everywhere. Same thing happens here. Cosine curves, sine curves, they are always continuous because you don't have to lift your pencil at all to get from one point to another point. Continuous graph. But I would like to talk about some of these things algebraically, and I'm hoping that when we talk about these, you guys will see how much similarity there is to these with just talking about breaks and asymptotes and graphs. All right, so f of x is equal to 1 over x squared minus 9. Well, really what you need to do is you need to study the domain of this graph. 1 over x squared minus 9. Factor the bottom, x squared minus 9. What value of x is going to make this bottom 0? Because you can have 0 in the bottom of a fraction. So hopefully you look at this x squared minus 9 and you recognize that that really means 1 over x plus 3 times x minus 3. Are you okay with the factoring there?
Yeah.
All right, so what value of x is going to make this 0? So the values of x would be 3, a positive 3, and a negative 3. So we call this a discontinuous graph, and the values of x that are making it not continuous are 3 and negative 3. Why are we calling this non-removable? Not because there's more than one. What happens is that it doesn't cancel out with anything in the numerator, and because it doesn't cancel out with something in the numerator, both values on the bottom are going to be non-removable zeros. Graph that on your calculator. Go to y equals, type in 1 divided by, make sure you put parentheses around the x squared minus 9. Type in 1 divided by, in parentheses, x squared minus 9. Make a graph. Some of your calculators will draw in the asymptotes. Some of yours won't. I'm not sure which ones do and which ones don't. The black ones do draw them in, the other ones do not. Is that right?
Yes.
Okay. So, you have a graph that So you get this graph that does this. You have a couple of asymptotes here. Now, if you have a not black calculator, those lines are not drawn in for you, but if you do have a black calculator, yeah?
Is there a way that we can show it?
I don't think so. I don't think you can, if it doesn't do it, it doesn't do it. I don't think I've ever been able to figure out how we can make that happen. So your graph kind of looks like this. Kind of doing this. If you zoom in, if you narrow your window down a little bit, you've got a graph that does this. And then in the middle here, you've got that going on too, roughly. Non-removable, because there's no way that we could get that graph to make one continuous curve. Unbounded behavior. Do you understand what I'm saying?
Yeah.
Okay. Non-removable. But really, the skinny of it is that it doesn't cancel out with anything on the top. Nothing cancels out, so it's not one quick fix. There's a couple of things going on there. Question?
Yeah.
Yes.
How did you know it was discontinuous before you?
I knew it was discontinuous because I could find values of x that would make the bottom of this thing 0. So it's always going to be discontinuous if there's a problem in the bottom of the fraction. If there's some place that the graph would be undefined, it's not continuous. The question is it removable or non-removable? In this case, nothing cancels out with the top, so they're non-removable. We can't fix it. Right? John? All right, f of x equals x over x squared minus x. Well, there's definitely going to be a domain issue. There are some values of x that we could type into the bottom, that we could put in for x in the bottom, that would make the function not defined. So x squared minus x. What I did, I wrote the function down again, x over x squared minus x. I factored an x out of the bottom. Do you understand that? They both have an x. I factor an x out. I'm just exploring the denominator right now. So I factored an x out. It left me with x minus 1. So what two values of x would make the denominator undefined? If you put in a positive 1, if we put in a positive 1 for x. Also, if we did what?
0.
If x was 0. If we replaced this x right here with 0, and we went 0 times something, we would have 0 on the bottom again. So, it is not continuous. Are you okay with that? Discontinuous. The graph is discontinuous. It is removed. We have a removable situation and we have a non-removable situation. It is removable if it cancels out with the numerator. Does it cancel out with the numerator? Yes. These two things right here cancel out. So we got rid of the zeros. So we have a removable situation at x equals 0.
So if you can remove the top, it's removable. If you can't do the bottom, that's
Yes.
Okay.
Yes. But see this x minus 1? Does that cancel out with the numerator?
No.
It does not. So that is considered a non-removable situation.
What did
Okay.
X do with that?
She asked me, I think this is what you asked me, if you can cancel it out with the numerator,
It's removable.
it's removable. You cannot cancel it out with the numerator, it is not removable. So you should be able to look at a graph and tell me if it's removable by that really quick fix. Can I move 1 point? Can I move 1 point? If I can, it's removable. If I can't move that 1 point, it's not removable. And now we're looking at some techniques that you can use to explore. So if you don't have the graph sitting in front of you, if you just have the equation, what can you do with it to make it not removable or removable? All right, number 7, I think the last example up here, f of x is equal to the absolute value of x minus 5 over x minus 5. Is it continuous? Is it not continuous? And are there any removable situations? Well, we need to talk about that, because when you see an absolute value in a graph, that's going to, well, first of all, go to y equals and type this in. Type in the absolute value. Do you remember how to get absolute value on your graph?
No.
Okay, do this. Go to y equals. And you press math. Press math. Arrow to the right to where it says num.
Okay.
And I think it's option number 1, abs. So this is what's going to show up on your calculator. Abs. put a set of parentheses there. We are taking the absolute value of x minus 5. Absolute value of x minus 5. Finish your parenthesis, and then divide it. But we have to divide it by this quantity. So make sure when you divide, you put the x minus 5 in parentheses as well. Yeah, and you're definitely going to have a break. Definitely, definitely. So press graph, and I think when you look at the graph of this, it looks, if you go to an x value of 5, you've got the graph headed this way.
Yeah.
And then if you go down here to the left of 5, your graph is headed this way, correct? All right, removable or not removable? Not. Graph is broken. We have to move this whole side up in order to make it removable. So it is not removable. It is discontinuous. It is a discontinuous graph. Non-removable at an x value of 5.
I don't like how my calculator shows the line.
Does it? I think I tried graphing this and it looks like it's connected right here.
Yeah,
Yeah, I don't like that either.
it confuses my head.
Yeah, but you know what? If that happens and you want to know what's going on at 5, go to a table. Go second graph and go to that value of 5, and it should say undefined, which means there's nothing going on there. In fact, we've got 2 holes. You should have 2 holes right here, and this line shouldn't be there at all. That line connecting them. I don't know why it does that. Sometimes the calculator is very smart, and sometimes it's not very smart, okay? But you also could look at the denominator and just know, okay, well, if I put in a value of 5 there, I'm going to get 0 on the bottom of this, okay? Yes.
It's discontinuous because it doesn't meet the criteria, right?
Yes. And another way to look at this too would be that there is not, well, I guess if you put 5 in here, you would have 0 over 0. Okay, so that's a bad example. Yes, I would suggest, whatever in doubt, you guys remember we talked about there's always 3 ways that you can check if a limit exists or it doesn't exist. And the 3 ways are to make a table, make a graph, or to use algebra. So when in doubt, I mean, some of these things, like this kind of stuff, you should be very comfortable with the algebra. But situations like this, when you're not as comfortable, look at your graph and explore some options that way. Okay? Can you always use a graph? See, that's the thing is like some problems I would say that that's okay, but then there's sometimes I feel like you need to be able to prove to me that you can do the algebra too. Okay. All right, I think right now I want to stop. What? What's the matter?
Nothing.